Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to today's lecture on advanced transition metal organometallic chemistry. We have been discussing half sandwich complexes of transition metals in the last few lectures, and in this regard we have discussed about transition metal cyclopentadienyl carbonyl complexes and transition metal cyclopentadienyl nitrosyl complexes. These nitrosyl complexes are the ones that we had just started towards the end of the last lecture, where we looked at the electron donating abilities of nitrosyl as a ligand. Now, nitrosyls or NOs can bind to ligand with 1 electron, or it can bind to ligand using 3 electrons. Now, depending on how it binds to the transition metal, it can exhibit a linear geometry or a bent geometry. Now, we have looked into these nitrosyl ligands electronically as equivalent to carbonyl ligands. For example, 3 carbonyls can be substituted by 2 nitrosyls, or 1 carbonyl can be substituted by 1 nitrosyl, but having a positive charge, and all of these can be correlated to the total valence electrons of each of these ligands. Now, continuing further in today's lecture, we are going to discuss on transition metal nitrosyl complexes in more details, particularly from the point of view of their preparations and reactivity. So, today we are going to be talking about various examples of transition metal cyclopentadienyl nitrosyl complexes that exist are cyclopentadienyl vanadium carbonyl dinitrosyl, or CO2NO, or plus. So, there are a variety of nitrosyl complexes which contains cyclopentadienyl as well as carbonyl and nitrosyl moieties. There are complexes which are exclusively binary nitrosyl compounds, for example, chromium NO4. So, this is a binary nitrosyl compound and not a half sandwich compounds like the ones which are shown over here. For example, also there are nitrosyl carbonyl compounds like so. What we see is the fact that there are several combinations of different ligands which including that of nitrosyl, which can make transition metal complexes. These can be half sandwich complexes where you have cyclopentadienyl ligand, carbonyl ligand, nitrosyl ligand making this kind of complexes, or it can be just manganese trinitrosyl monocarbonyl complex where there is no cyclopentadienyl ligand, or it can be even simple binary nitrosyl compounds, for example, as in chromium tetranitrosyl. Okay. So, having seen this, what comes to the fore, next is that one should find a ways and means for preparing these complexes, and the preparative pathway is quite intuitive and simple, in the sense that these nitrosyl complexes can be prepared from their cyclopentadienyl transition metal complexes by direct treatment with NO. For example, in the previous case where we had seen preparation of half sandwich cyclopentadienyl transition metal carbonyl complexes, one of the effective method was just taking metallocene and adding CO gas to make this kind of half sandwich complexes. Analogous to that strategy, a similar strategy is in place for preparing this cyclopentadienyl metal nitrosyl complexes, where the metallocenes are directly treated with NO gas to get these complexes. Let us we will illustrate this with a few examples. For example, here we have nickelocene giving C5H5NiNO, or one can take 2 C5H5 CO2 plus twice NO, giving 4 carbon monoxide and H5CO NO dimer, as well as C5H5 rhenium tricarbonyl plus a source of NO plus H SO4 minus in dichloromethane eliminates a CO to give C5H5 rhenium CO2 NO plus and HSO4 minus. Now, all of this reaction has a commonality, and commonality is that these are either binary metal cyclopentadienyl complexes or half sandwich metal cyclopentadienyl carbonyl complexes by reaction with NO, giving these cyclopentadienyl transition metal nitrosyl complexes. Now, that is a similarity over here. Another similarity for the last two reaction is the fact that carbonyl moieties are getting replaced by NO in each of these reaction. For example, in this reaction the 2 carbonyl gets replaced by NO, whereas over here one of the carbonyl gets again replaced by NO. So, what does that indicate? That it indicates probably is that NO can successfully replace carbonyl, in a sense that probably binds more strongly than carbonyl, and also This kind of is very informative in the sense that we have this belief that CO binds quite strongly to transition metal. So, from that perspective, if something were to displace even CO bound to transition metal, that only indicates that NO probably binds more strongly to CO, so that it can successfully replace already tightly bound metal bound CO for making this CP transition metal nitrosyl complexes. So, having seen the preparation, there is not much variety in terms of synthesis of the cyclopentadienyl transition metal nitrosyl complexes, given the fact that there is only one kind of preparation that involves these metal cyclopentadienyl complexes with NO, as is shown over here, for preparing this transition metal cyclopentadienyl nitrosyl complexes. So, this indicates that there are not many route available for preparing these complexes other than the one which are shown over here. So, next we move on to some important aspect of this nitrosyl binding to transition metal, particularly the structure and bonding of these nitrosyl ligand. Now, nitrosyl like CO can also be bridging as well as terminal, but it also has another dimension that it can be bent or linear. So, like CO carbon monoxide can be bridging or terminal, and also the second variable is NO can be bent or linear upon binding to transition metal, and this is correlated to the type of binding that the NO exhibits with a transition metal. For example, in a linear binding, NO is a 3 electron donor, 3 donor in linear binding, and it is 1 electron donor in bent binding. So, to illustrate this further, metal bound bent MO would look like something like this, whereas a linear is something like that, and this binding of the bent or the linear form can be characterized by this angle or angle MNO, which is around 180 degree for the linear ones, and the same angle the angle MNO would be significantly shorter or smaller than 180 degree if it were to be a bent binding. Now, these can be the bent or the linear form of binding can be easily discerned from the extracrystallographic single crystal experiments, whereby one can measure the angle at nitrogen in the bent and the linear form of transition metal MNO metal nitrosyl complexes. Let us now look at some of the cyclopentadienyl nitrosyl complexes which have been structurally characterized, and look at the binding frequencies, IR frequencies of this metal nitrogen interaction bond to sort of to sort of get some insight as to the type of binding they exhibit. For example, this dichromium nitrosyl complex, cyclopentadienyl nitrosyl complex, as is shown over here, so here the markers are the chromium nitrogen bond is about 169 picometer, the nitrogen oxygen bond 118 picometer, and this bridging nitrogen oxygen bond is 119 picometer, and this chromium nitrogen bridging chromium nitrogen bond is 196 picometer. So, one can see that the bridging chromium nitrogen and the nitrogen oxygen bonds are longer than the terminal chromium nitrogen bond, which is 169 versus 196, 196 versus 169, and NO sort of remains almost the same with 119 picometer as opposed to 118 picometer. Whereas these angle at the linear one is quite close to the angle at the linear one is quite close to 180 degree, which is about 176 degree. So, this molecule has several NO stretches. For example, nu NO linear is nu NO linear is 1677, nu NO bridging is 1518, whereas nu NO free is 1876 centimeter, and nu NO plus free is 2250 centimeter inverse. So, here is a molecule in which both the bridging as well as the terminal NOs can be seen. There are two bridging and two terminal. Not only that, the terminal ones are in a linear form. That means these terminal NOs are being bound as a 3 electron donor. In this molecule, however, there is no bent terminal NOs observed over here. There are only two types, one is bridging and the linear, and they can be characterized by different frequencies. For example, the bridging NOs appear at a lower wave number than the terminal NOs. Now, we will take a look at a few such examples which will clarify the point. For example, this ruthenium, another ruthenium complex which has no bridging nitrosyls, but two terminal nitrosyls. However, one of the terminal nitrosyl is linear, whereas the other one is bent. So, we will see that here we have a ruthenium complex which has a bent terminal NO and a linear terminal NO, and it has one chlorine and one phosphine. The metrical data are as follows. So, the NO bond as expected is around 117 picometer. N ruthenium metal ruthenium bond ruthenium nitrogen bond is about 185 picometer, and for the bent NOs, whereas it is 174 picometer for the linear NO, and nitrogen oxide NO or distance is 116 picometer. This ruthenium nitrogen oxygen angle is 178 degrees, whereas in the bent one it is 138 degrees. Now, what is interesting is the fact that one can sort of correlate these bond distances with the electron donor ability of this NO ligand. For example, a linear NO is a 3 electron donor, and hence it forms a stronger bond with ruthenium as opposed to the bent NO, which is a 1 electron donor, and as a result what we see is that ruthenium nitrogen bond in a linear terminal NO is indeed shorter at 174 picometer than that of 185 picometer, which in bent NO, which is a 1 electron donor. So, this sort of this X-ray data sort of verifies the nature of bonding, or corroborates the nature of bonding, which sort of suggests that a linear NO would be a 3 electron donor, making a stronger bond, resulting in a shorter metal nitrogen distance in comparison to that of a bent NO, which is a 1 electron donor, and then that would be of a longer ruthenium nitrogen distance. So, for example, let us look at the infrared frequencies over here too. New NO linear is 1845 centimeter inverse. So, this stretching is 1845 centimeter inverse, whereas new NO bent is 1687 centimeter inverse. So, one can really see in this case as well that the bent one is of a longer bond length, 1 electron donor, and hence a weaker bond. So, a lower energy is required for the stretching of this bond, which is 1687, whereas the linear NO is a stronger of the two NO interactions and involves 3 electrons. It has a much shorter ruthenium nitrogen bond distance, and as a result it has a higher 1845 centimeter inverse as the stretching frequency. So, what we see over here is a nice demonstration of IR as well as X-ray corroborating each other and sort of indicating the type of interactions these metal nitrosyl compounds are showing. So, we are going to look at some more of these examples that will further highlight this point of infrared spectroscopy and IR spectroscopy corroborating each other in the characterization of metal nitrosyl interaction is in various half sandwich transition metal nitrosyl complexes. So, here we have another nickel cyclopentadienyl nitrosyl complex, which contains only one type of linear metal nitrosyl bond. I am drawing the complex over here. So, this has a linear metal nitrogen bond. The nitrogen oxygen bond distance is 117 picometer, which we had seen, and nickel nitrogen is 160 picometer. This angle is linear, so it is about 180 degrees, and the correspondingly the stretching frequencies are as nu NO linear is 1830 centimeter inverse. So, this is quite higher energy, indicating that this is a 3 electron interaction. Now, we are going to take up another example containing 2 cyclopentadienyl ligands bound to molybdenum in a eta 5 fashion, and eta 1 bound cyclopentadienyl ligand bound to molybdenum, and the fourth ligand being a NO ligand bound in a linear fashion. So, let me just draw this complex over here. So, Cp molybdenum, Cp NO H. Now, this NO distance in this complex is 121 picometer, and molybdenum nitrogen is 175 picometer, whereas this angle is close to being linear, 179 degrees. So, the corresponding frequency is nu NO linear is 1610 centimeter inverse, and this molecule is highly fluxional at room temperature. So, with this I would like to conclude today's lecture. In this lecture, we have been looking into half sandwich complexes of cyclopentadienyl transition metal nitrosyl complexes, particularly with respect to their synthesis, these as well as structure and bonding. These complexes are usually prepared by mainly one type of method that involve cyclopentadienyl transition metal complexes by reaction with NO gas or NO source, giving the cyclopentadienyl transition metal nitrosyl complexes. We have also looked into the binding of these nitrosyl complexes, and what we found that this nitrosyl ligand, similar to what had been observed for carbon monoxide, can bind in both bridging as well as terminal forms, and also within there is another additional versatility of this NO binding is that within its terminal binding, it can exhibit a linear or a bent form. Now, linear form arises due to 3 electron donation of NO to the metal, whereas the bent one arises due to 1 electron donation of the NO to the metal, and as a result of this, the number of electron that is being donated to the metal, the bond becomes stronger in case of the 3 electron donor, and that is reflected in a shorter metal nitrogen bond in the metal NO moiety, and that also reflects in a relatively higher MNO stretching nitrosyl stretching frequency for these complexes, whereas in the bent one, since it is a one electron donor, metal nitrogen bonds are relatively longer, and as a result the new stretching frequencies for the bent terminal nitrosyls are occur at lower wave numbers. So, with this I would like to conclude today's discussion on metal nitrosyl complexes, cyclopentadienyl nitrosyl complexes. We are going to be discussing some more on these transition metal nitrosyl cyclopentadienyl nitrosyl complexes into the beginning of the next lecture, and then move on to another new type of half sandwich complexes, which are cyclopentadienyl transition metal hydride complexes in the next lecture. So, I thank you for patiently listening to this today's lecture, and I look forward to being with you in the next lecture. Till then, goodbye.